My dear student, in the previous video, I have started to solve the problem number 9 in the exercise 12.1. In the problem 9, I have verified two properties of the algebraic structure, that is closure property and commutativity. So, M is the set of all matrices of the form x such that x is an element in R minus 0. In the real number set, except 0, you can consider all the real numbers. And keeping that x as elements of the set of matrices M, in binary operation, matrix multiplication. Binary operation is matrix multiplication. Matrix multiplication. Under this operation, binary operation, matrix multiplication, and the set M consisting of all 2 by 2 matrices of the form x, where x is the real numbers except 0. I have proved a star is defined on M, that is, the star is closed on M, that is binary operation. We have proved closure property, and also commutativity also have proved in the previous video. Now I am going to prove the associative property. Associative property. This is in the exercise 12.1, problem number 9. Associative property. For that, we have to consider three matrices of the form X is a matrix X, and X. Y is a matrix Y, and Y. Z is a matrix of the form Z. Like this, the three matrices, matrix X, Y, and Z belongs to the set M. We have to prove that X star, Y star Z. So Y star, first you keep X as it is. Y star Z is Y into Z. This is X star, Y star. You know this is X star. Y into Z, that is Y, first row, first column, Y is Z. Y into Z, Y is Z, first row, first column, Y is Z, 2 Y is Z. As we multiply in the previous commutative property, Y into Z, Y is Z, plus Y into Z, Y is Z is 2 Y is Z, first row, first column. Similarly, first row, second column, Y into Z, Y is Z, plus Y into Z, Y is Z, that is 2 Y is Z. And again, here also 2 Y is Z, and this is 2 Y is Z. This is Y star. Now, extra Y star, that is X, and Y star is 2YZ, 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 and 2YZ. That is total multiplied first row, first column. Here also, uniform multiplication, matrix multiplication of these two matrices, X and 2Y is the 2. This here first row, first column. X into 2Y, that is 2Y is that 2XY is there. That is equal to first row, first column. Here, X into 2Y, that is 2Y is there. 2XY is there. x, first row first column, x into 2y that is 2xy that. And first row first column 2xy and this is element x into 2y that is 2xy that plus 2xy that. Like that first row second column x into 2y that is 2xy that plus first row second column 2xy that. Like that second row first column 2xyz plus 2xyz. Here also 2xyz plus second row second column is also 2xyz. That is what you get 4xyz plus 4xyz 2xyz plus 4xyz 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 4xyz. So each and every element of the form xxx only. The elements are 4xyz, 4xyz, 4xyz and 4xyz. This is equal to 2 plus 2, 4xyz, 4xyz, 4xyz and again 4xyz. So it is of the form of the matrix M. It is also of the form xxx, therefore it belongs to M. Therefore this is x star, y star is that is, this is the matrix. Now, right hand side, this is left hand side, x star, y star is it. Now, we have to prove x star, y star is it. Now, I am going to prove x star, y star is it equal to x star y, already we proved 2xy, 2xy, 2xy into 2xy. X star y is x 2xy into 2xy, 2xy. Because in the commutative property also we proved x into y, x, this is y, that is 2xy, 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 2xy into z. Z is z. That is equal to, again, 2x into z is 2xyz plus 2xyz, first row first column, first row second column, 2xyz into 2xyz is 2xyz, that is 2 plus 2xyz is 4xyz, this is 2xyz, second row, first row second column, 2xyz plus 2xyz is 4xyz, similarly second row first column, 2xyz plus 2xyz, 4xyz, second row, second column, 2xyz plus 2xyz is 4xyz. This also, this is left hand side and this is also belongs to the set geometry, right hand side. These two are equal. Therefore, x star y, x star, left hand side is x star y star is z equal to x star y star is z. It is proved. Therefore, hence associativity. Hence associative property is true in the set M. Associative property is true in the set M. Also, the ninth sum in the second part, they are also find out, they ask you to find out the identity and inverse in the same set M. Existence of identity and existence of inverse. Now, existence of identity, you will see. Existence of identity. Existence of identity. This is ninth problem, second subdivision. Existence of identity. For matrix X, you know the matrix X, 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 X. We can find a matrix E. Is E, the element E which belongs to M, is the identity matrix. We consider E is a matrix. You can consider a capital E. Capital E is the matrix. Is the identity matrix. That is X star E equal to X, by the definition of identity matrix, X star identity equal to the matrix X itself. X is X, 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 X into E is E, matrix multiplication. It is equal to given X, X, X. By the definition of identity, a matrix with identity is the matrix itself. Therefore, X star E equal to X. Matrix with identity is the matrix itself. Therefore, we have to find out what is E, identity. So this is X star E, first row, first column, first row, second column, that is XE plus XE, 2XE. This is 2XE, 2XE, and 2XE equal to X, 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 X. So, comparing the element, we can find E. 2XE, and the left hand side element equal to right hand element is X. 2XE equal to X. From this, I can get E equal to X, X cancel on both sides, E equal to 1 by 2. Because this X, right hand side X, cancel, 2E equal to 1, E equal to 1 by 2. From that, write one more step. If you want, X cancel on both sides, this is 2E equal to 1, E equal to 1 by 2. Therefore, the identity E is equal to 1 by 2, 1 by 2, 1 by 2, 1 by 2. Because E is 1 by 2. Instead of 1 by 2, 1 by 2, 1 by 2, 1 by 2, I can replace by E. It is also the element in the set M. Therefore, this 1 by 2, 1 by 2, 1 by 2, 1 by 2 is the identity element in the matrix set, given matrix set M. Therefore, which is the identity. Which is the identity element. Identity in M. Next, finally, inverse element of the matrix X. Existence of inverse. Existence of inverse. X is a matrix, X, 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 and we can find X inverse is a matrix Y is the inverse of X in the matrix set M. Suppose X inverse is the in Y of the form X is the inverse of M. X in the set M. We can find out by definition, an element and its inverse is the identity, you know. We know that by the definition, X star X inverse equal to identity E. X is X, X inverse is Y. Star is multiplication of matrices. E is 1 by 2, 1 by 2, 1 by 2, 1 by 2. By usual multiplication of two matrices, we have to find out the inverse Y. Inverse element Y. How can you find? By the usual multiplication, 2xy plus 2xy, xy plus xy, 2xy. Here also you get 2xy. First row, second column, first row, first column, 2xy, second row first column, second row second column. It's also 2x equal to 1 by 2, 1 by 2, 1 by 2, 1 by 2. Because this is the identity. An element and its inverse is the identity. That is the definition of inverse element. So, comparing the two elements, 2xy equal to 1 by 2. We want y. Y equal to 1 by 2 into 2x is 1 by 4x. 2x, while you bring it to the right hand side, it becomes the denominator, 1 by 4x. Y equal to 1 by 4x. Therefore, x inverse is 1 by 4x, 1 by 4x, 1 by 4x, 1 by 4x, which is also in the set M. So x inverse 1 by 4x, 1 by 4x, 1 by 4x is the, which is the inverse of the element x. Hence all the properties are satisfied by the binary operation, matrix multiplication with the set M. That is the problem 9. Okay, I will stop here and I am going to continue the 10th problem in the next video. Thank you.